begin. Today we'll look at a very important topic known as Thevenin and Norton equivalent circuits. Okay. Before that, just last remaining example or last remaining slide on source resistances. So let's look at that first. At the end, it might go a few minutes past 3 o'clock. So if you will have to leave, you can leave. I'm just going to continue recording until I cover all the material for today. All right, let's see. 3 methods finding Thevenin Norton. All right, so we looked at sources, we looked at source resistances. Just want an example of how a real life battery has resistance. The resistance is very small, okay, not large enough just to be measured by normal methods. So we use a slightly different technique to measure that resistance. So we have a battery. The electrical model for the battery is a voltage source in series with a resistance Rs. It's a sealed box. We cannot probe inside this box, right? That resistance is noted as Rs, and we're applying a test current at its output terminals. Right here. Now this test current is applied in the form of a pulse, a step-up pulse. Okay, it's known as a step input because this is a step up, going up here and down here. If it goes up like that, kind of like a vertical line, it's known as a step up. If it comes down, it's step down. Anyway, this is known as a step input. Okay. And what it's doing is we are looking at the test current, applying two different values of the test current, I test, and we are measuring the response of the battery at the output terminals. So we're measuring the voltage that we obtain as a result of applying this current. And then what we can do is apply Ohm's law from the measured change in voltage in response to the applied change in current. So what we are doing here is we apply current I or I test as I1 at this level, and we change the value all the way up to I2. When we apply I1 and measure the voltage, that voltage can be found by applying KVL. The internal voltage of the battery is Vs. If we have current Is flowing through that circuit, it's going to cause a voltage drop across Rs. So the voltage measured at the output terminals can be found by applying KVL. Vs minus Is times Rs. Since we know Vs and we know I1 is the voltage current that we are applying, we can find the value for that voltage. Now we change the test current. When we change it, we know delta I, and then we measure the change in delta V. Delta V will change because if the current increases, then the voltage drop across that resistor is going to increase. If the voltage drop increases, then the total output voltage decreases, and so it steps down. And we take the delta V and delta I, apply Ohm's law, and we can calculate the series resistance of that battery. For a standard Energizer alkaline battery, it turns out it's 0.15 to 0.3 ohms. Very small, less than half an ohm. It's probably a quarter of an ohm, right? 0.15 to 0.3. So 1/4 of 1 ohm, very small. All right. So there is this graph on this data sheet. There's a graph that shows a change of a voltage from 1.45 to 1.378 in response to a change of 0.5 amps. We apply the same principles and we can calculate the resistance for that battery as 0.2 ohms or 0.214 ohms. Okay, 0.214. So if you have 3 such batteries in series, what do you think is the series resistance and the voltage? The answers are given to you. I'm assigning this as student practice. See if you can arrive at those answers. Okay. Good. All right. Okay. So Thevenin and Norton. When are your labs? Somebody has it today, 3 to 6. All right. And then tomorrow. So Thevenin and Norton, that's what you're going to do. All right. So Leon Charles Thevenin was a French telegraph engineer in the late 1800s. He was working with electric circuits, and he postulated a theory. His theory was that if you have a large linear circuit comprising of multiple sources, voltage sources, current sources, and a number of linear components like resistors, you or we could represent that entire circuit between any 2 pairs of terminals as a single voltage source. That was his theory. The theory came to be known as Thevenin's theorem, and it's one of the most important topics in circuit analysis. Okay. Now, real life source has a resistor in series. So Thevenin's theorem states you could take a large linear network and represent it as an equivalent voltage source in series with a resistor. The voltage source came to be known as Thevenin voltage. Resistance came to be known as Thevenin resistance. And that, in short, is the Thevenin theorem. A few decades later, there was an engineer by the name of Edward Norton, who's working at Bell Labs. Not the actor, he's not that old. This was around the 1910s, 1920s, and he was working with a lot of audio equipment, Bell Labs, so Telefonia at the time. And he was working with a lot of current sources. So he postulated his own theory based off of Thevenin's theorem, stated that you could take that same circuit and you could represent it as a single current source. Okay, instead of a voltage source, you represent it as a current source. Of course, current source has a resistor in parallel. So the circuit came to be known as Norton equivalent circuit, which contains a equivalent Norton current source in parallel with a Norton resistance. The Norton resistance, by the way, is the same as the Thevenin resistance. No difference. Okay. And so, let's go here. Thevenin and Norton. Okay. Thevenin equivalent is a voltage source in series with a resistance. Norton is a current source in parallel with a resistance. Let's go here. So let's say you have a electrical system. Electrical system has voltage sources and it has some current sources and it has passive resistors. Now, obviously, we have seen previously that if we can represent a large circuit comprised of multiple resistors as one single resistor, it simplifies our calculations. And we can use that as an analysis technique. So we find Req. That Req for the circuit between those pair of terminals is Thevenin resistance. Okay. Now, you have the circuit and you have another circuit, interconnected load, that is connected between those two pair of terminals. And so these are the terminals of analysis. Or the terminals of interest. Or you could also say they are output terminals. Does not matter what we refer to them, how we refer to these terminals. We are analyzing the rest of the circuit between those 2 points. Okay. Now, in a circuit, there are multiple nodes, so we can find the Thevenin circuit between any 2 pairs of nodes, and they'll all be different, right? Req is different from the perspective of any 2 points. This is such as the same thing. So, if we have a complex circuit, we want to reduce it. What we obtain is Thevenin and Norton equivalent circuit. So we have equivalent voltage source, equivalent current source, and we have the equivalent resistance, Req. Req, the method for finding Req has not changed. It's still the same, right? That's still the same. And then we'll go through and we look at techniques on how to determine how to add up voltage sources, how to add up current sources, what is permitted and what is not permitted. But let me start with a real life, not real life, like an example. If you were to perform this on the lab, okay, and the measurement part is actually easy. It's the theoretical part that takes long. Okay, so let's say we have a circuit comprised of 1 voltage source, 5, 6 resistors, right? And we have a pair of terminals where we are trying to find the Thevenin circuit. So if you have 2 terminals that are open, you have to measure between those pair of terminals, right? Or determine the Thevenin circuit between those pair of terminals. What do? All you have to do is you have to measure voltage, you have to measure resistance, and you have to measure the current between those pair of terminals, right? The voltage measured at those terminals is the Thevenin voltage. The current flowing between those 2 points is the Norton current. And the resistance measured between those 2 points is your Thevenin resistance. In a lab, if I was to do this procedure, it would take me less than 2 minutes. It would take you less than 2 minutes. And I'll explain why. If you wish to measure voltage, what do? Take our meter, take the 2 terminals of the meter, connect to those 2 points, right? So if we have a circuit, we want to know what the Thevenin voltage is between any 2 points. You take a meter, measure the voltage. That's it. That's your Thevenin voltage. Now you keep those 2 connected at those 2 points. Now, if you wish to find the Norton current flowing between those 2 points, what do we need? We need a short circuit. We need a pathway between those 2 points so that current can flow through between those 2 points. Well, if the meter is still connected and we change the setting to measure current instead of voltage, what does it do? The meter now has very low resistance. In voltmeter mode, it has infinite resistance or very large resistance. In current measurement mode, it behaves like a short circuit wire, right? We don't need to do anything. Simply keep the meter connected between those terminals, change the front panel from voltmeter to ammeter, done. Current measured is your Norton current. No need to change anything. Well, we still got a voltage measurement terminal is separate from current, so you got to pull it out and plug it underneath. But other than that, nothing else to be done to the circuit. And then Req, still measured between the same terminals. You remove the voltage supply, place a short circuit wire in there, measure Req, done. That's your Thevenin resistance. So actual measurements can be done in less than 2 minutes. The theoretical calculations and understanding what it is, that's what you're going to talk about. Okay. All right, so let's first talk about voltage sources. If you have multiple voltage sources, how do we reduce them down to one single one? Well, like with all things voltage, we apply KVL. So let's say we have 2 batteries, right? Batteries are rated for 1.5 volt, standard ones at least. So 1.5 volt, 1.5 volt. What is my V out? Three volts. Find it by applying KVL. So V out is going to be 1.5 plus 1.5. Therefore, V out is 3 volts. So if you have 2 voltage sources connected in series, the Thevenin voltage is the sum of both voltage sources. Make sense? How about now? What is V out? Absolutely 0. Once again, if you apply KVL, you can see it's 0. So just because the statement says voltage sources connected in series will sum up, doesn't mean we can ignore KVL. KVL will must always hold true. Okay, so the reason we are adding them up is because they are plus minus, plus minus, plus minus. So if they're stacked in series like that, then you can add up the voltages, right? Nowadays, all devices come with built-in batteries, but in my day, we used to have remote controls and other devices. We had insert batteries in them. Anybody ever done that? If you used an Amazon device, they still have some batteries. So yes, you connect 2 batteries in there, and then they are both connected in series. So you have 1.5 volt plus 1.5 volt, you get 3 volt at the output. I have an older device going back to 15 years. That remote control takes up to 3 batteries, sorry. And so 3 batteries in series gives us 4.5, right? So anytime you connect batteries in series, that's what you get. What's V out now? I had 3, I had 1.5. Only one is correct. It is 1.5. Because if you apply KVL around the loop, 2 voltages are added up and 1 is subtracted. Especially given this polarity, right? If you apply KVL and you measure V out with plus at the top and minus at the bottom, the 1.5 plus 1.5 and then minus 1.5. So that gives us 1.5 as measured with this polarity. If the signs for those were flipped, if this was connected like this, so it's plus and minus, and you're measuring voltage this way, this we have to be minus 1.5. Let's take a pause. Let me know if you have any questions. This is not really related to the Thevenin voltage. Well, it is related, but I just wanted these examples to show students that just because they are stacked and connected in series does not mean that the voltage will always add up. Okay, it is based on KVL. So it's also based on how we are connecting the sources. Any questions? Okay. So if voltage sources are added up, what about resistances? Well, ideal sources do not have any resistances, but real life sources do. So real life limited source will have resistors. We can simply add up the resistors as if they were in series, not as if they are in series. And then VTH, again, adding up the voltages in series. Okay. So if we have a circuit like this, it's far easier to reduce it and find Thevenin voltage and Thevenin resistance. So that was series connection. Series connections are straightforward. Parallel ones, not so much. We cannot connect voltage sources in parallel because it violates KVL. You cannot have two separate voltages with two separate values connected together. If you have a 1.5 volt battery and you connect it to a 3 volt battery in parallel, it violates KVL. That connection is not permitted. Here's the thing. Current always flows from high potential to lower potential. So if you have a 3 volt battery connected in parallel to a 1.5 volt battery, the 3 volt battery is a higher potential. So it's going to start flowing or supplying energy to the other battery. Okay. If that is not controlled, then a reaction takes place where a lot of energy is expended, a lot of heat is generated, and because of the generated heat, it could cause a short circuit, cause a fire. Okay, so that reaction must be controlled. This is something we do all the time, though, in general. Like battery chargers, what we are doing is we are actually connecting an external battery source to our device, and we are charging our batteries from that external source, right? So we have two dissimilar voltage sources connected in parallel, but that reaction or that circuit is controlled. All right. But in general, if you have two ideal sources like this, ideal sources cannot be connected in parallel because there is no resistance in there to control that circuit. Does that make sense to everyone? Right? Yes. So question being asked is, why wouldn't this hold constant? Right? Current always flows from higher potential to lower potential. So if we have a circuit where if this is 1.5 volts, meaning this point right here is at 1.5 volts, and this point is at 3 volts, and you connect them together, well, current is going to start flowing from high to low. It's going to start flowing that way. And that's why it also mathematically, if you apply KVL around the loop, it will not work. 1.5 is not equal to 3. That violates KVL, just mathematically speaking. But in general terms, law of conservation of energy applies. If they were the same voltage, then no. Then it would work. Yeah, then it would work. Plus, this is only talking about ideal sources. Ideal sources do not exist. But as a concept, students should be familiar with this, right? Because in real life, we do this all the time, right? If you have a portable battery pack, we wish to charge our phones, we would connect a external battery pack that has a higher voltage and it's going to go into our phones to be charged. And so it works all the time. All right, so real life sources right here. Real life sources have resistances. So we have a means of controlling the flow of current. And so those connections are permitted. Okay, you have a means of controlling the current flow. So those connections are permitted. Thevenin resistance would be the parallel combination of R1 and R2. And the Thevenin voltage is a sum of V1 and V2. Is a sum of V1 and V2, but it's a fraction of V1 that appears and a fraction of V2 that appears between those output terminals. Okay, and there's a small, not a derivation, but an explanation that I can show in a couple of slides. Okay. So if you have two dissimilar voltages, you can add them up to find the Thevenin voltage. Okay. All right. If we have the same thing with a series connected current sources, if you have two ideal sources connected in series, well, we would not be able to apply KCL. Ideal sources would not work. Right? At this point or that node, KCL at this node will not work. One current entering would not equal the other current leaving, and so KCL is violated. But again, fortunately, this is an ideal current source, so we're not looking at ideal current sources. We need parallel connected real life sources that have resistors in parallel. Okay, resistors in parallel. So if you have two current sources and you connect them in parallel, let's say they are ideal, the total equivalent current is simply the sum of those two. This is I1 plus I2. I1 plus I2. And real life current sources have resistors in parallel. And so the Norton current is I1 plus I2, and the Norton or Thevenin resistance is the parallel combination of the two resistors, R1 parallel R2. Okay. All right. So similar to that example for the voltage source, what is the resulting Norton current for this? First of all, which direction is that current flowing? We have two current sources, 5 milliamps and 7 milliamps. So you connect them together and you apply KCL. Which direction is the resulting current flowing? How many say up? How many say down? How many say left? Anyone with right? Down is right. So you'll have 2 milliamps going in the downward direction. Simply means it's coming out this way. 2 milliamps. Okay. All right. So methods for finding Thevenin and Norton equivalents. Okay. And we're still writing the previous. All right, let's take a pause. Let me know if you have any questions thus far. Okay. All right. So 3 methods of finding Thevenin and Norton. First method is, of course, the most straightforward. We can simply take voltages that could be in series or parallel and add them up. If you don't, then we use something known as source transformation. So here, here's the introduction of a new technique. We say that we have a large circuit A and is equivalent to its Thevenin circuit, which is X. And then we also say A is equivalent to its Norton circuit, Y. So if A equals X and A equals Y, what can we say about the relationship between X and Y? They are the same, right? And so we can write if A equals X and A equals Y, where did that go? Okay. Therefore, I can write X equals Y. The Thevenin equivalent circuit between any 2 points is equivalent to the Norton equivalent circuit between those same 2 points. Okay. And so from this, we can introduce a topic known as source transformation. It simply states if you have a voltage source in a circuit, you can transform it into a current source and vice versa. But in order to do so, we need to have a resistor present in that circuit. So for a voltage source, we must have a resistor in series. And for a current source, we must have a resistor in parallel. We cannot perform source transformation without that being present. Okay. Because again, the whole concept is based on Thevenin and Norton. So source transformation. It requires a resistance. So if you have a voltage source, you can transform it into a and transform it into a current source in parallel with that same resistance. AB. Actually, this is a better representation. Source transformation can be tricky, so I try not to use it too much. I try to avoid it as much as I can. All right. So what the slide is showing us is here, we have two resistors in parallel, two sources in parallel. We can convert both of those into current sources by using source transformation. Okay, we convert it into I1 and R1 and I2 and R2. Use Ohm's law to find I1 and I2. Once we have those values, we can add up the two currents, find the Norton as V1 over R1 plus V2 over R2, and we can find Rn as a parallel combination of R1 and R2. Lastly, we perform a source transformation again to get the Thevenin equivalent. And to get the Thevenin equivalent, multiply these two, and you obtain this equation. And that kind of is the derivation for where that equation comes from. Okay. So you can do something similar for current sources and derive an expression. Come on, why does it do this? Okay. Answer is already given to you. You should be able to apply the same principles. All right, any questions? Okay. All right, so the other method, which is by far the most common method that I use to, whenever I teach these topics, is to find the open circuit voltage, the short circuit current, and the Req resistance between those pair of terminals. So here in this case, we have a voltage source and two resistances. And these are the terminals of analysis. Okay, these are the terminals of analysis. If you wish to find the open circuit voltage, we simply keep the output terminals open, analyze the circuit, and then determine the voltage between those pair of terminals. So this goes back to what I was saying. If you wish to determine the Thevenin and Norton circuit in real life on a bench, so in our lab benches, we have a circuit. We take the multimeter, we connect it between these 2 points. We measure that voltage between the open terminals. That open circuit voltage is our Thevenin voltage. Okay, measurement is easy. Analysis, of course, takes a little bit of work. Depending on the circuit, the analysis could be easy, straightforward, or it could be tricky and difficult. And then if you wish to find the Norton current, then we must place a short circuit wire between those two pairs of terminals and analyze the circuit again to calculate ISC, the current that flows through that short circuit. And that ISC is our Norton current. Okay. Three point. Does that make sense? Any questions? Again, this is one of the most important concept of circuit analysis. Okay. All right. RTH is shown as being derived or calculated from Thevenin voltage and Norton current, but I typically advise students against doing so. The reason is simple. We need to find three quantities: voltage, current, and resistance. We use Ohm's law, V equals IR. R is equal to V over I, or I is equal to V over R, either ways. So we are using two quantities to find the third. Well, what if one of our quantities is incorrect? So one of the two quantities is incorrect, then a third one will also be incorrect, right? So you get 2 out of 3 wrong. So we don't want to be in that situation. We want to be able to find Req independently. And for many circuits, it is possible to find Req independently. Okay. So we can use this as a verification to verify whether our answer is correct or not, but we do not use it directly to find the value for that resistance. We find VOC separately, we find ISC separately, and we find RTH separately, and all three quantities separately, and then verify them using Ohm's law. All right. Let's see. I'm going to end class here today because this is where we stopped for the earlier section. And so I like to keep everything in sync, as I've mentioned that before. And so we'll end class here today, and I will see you all on Friday. If you have any questions, feel free to ask.